Hi everyone and welcome to this interactive full course session by Simplilearn on computer networks. In this course, we will look into various aspects of computer networks. That is, a computer network is an interconnected system of devices to transmit data and information and to share multiple hardware and software resources. But before we begin, if you love watching tech videos, subscribe to our channel and hit the bell icon to never miss an update from us. Now, without further ado, let's take a look at the agenda for today's session. In this course, to begin with, we will understand what is Ethernet, which forms the basis of connection medium in a computer network. Moving on, we will look into difference between a switch, hub, and a router, which are the most three important networking devices. Moving on, we will look into network topology. Next, we will look into information regarding TCP and IP model. Continuing with OSI model, the DHCP explained distance vector routing protocol which helps in transfer of information and data over the network channel. Then we will look into what is an IP address, which is used to transmit data over the network channel. Moving on, we will look into difference between IPv4 addresses and IPv6 addresses. And at the end, we will look into circuit switching and packet switching. With this, we have completed all the basic parts of a computer network. Moving on, we will look into more complex headings, which are what is subnetting? Subnetting is a part of computer network which prevent the wastage of IP address in a network. Moving on, we will look into multiple networking commands which are helpful in troubleshooting network issues. Next, we will look into the user datagram protocol, also known as UDP. Moving on with stop and wait protocol, which forms the basis of transfer of information and data in a network channel. Using the application of stop and wait protocol, we have sliding window protocol and go back in queue protocol. As for the last heading for this full course, we have top 10 networking interview questions, which will prepare you for any networking related interview. Let's move on to the first heading. What is Ethernet? Ethernet is a form of communication network that uses a wired medium to connect devices for data exchange in a network. For example, LAN, also known as local area network. Also, WAN, known as wide area network. Ethernet also applies different protocol on the data to be transmitted over the communication channel efficiently and smoothly. Moving on, let's look into why to use Ethernet. As we now know, the Ethernet is a mode of connection for multiple devices to share and exchange data. But using this way of transmission also has its benefit. For example, the Ethernet network provides us with a high-speed connection for sharing data. Ethernet also provides the user data with a secure channel for transmission. The data that is transmitted over the Ethernet channel is reliable and has rarely faced any issues at the sender side. Let's move on to the next heading. Now we will look into different types of Ethernet. In general, the Ethernet is divided into three different types. First is the fast Ethernet. This type of Ethernet operates on a twisted pair cable with a data transmission speed of up to 100 Mbps per second. Fast Ethernet connections are used for personal connections or used in companies that require low internet connection. Moving on, we have Gigabit Ethernet. This connection is used for high-speed internet connection with a speed ranging from 1000 Mbps to 1 Gbps. It is an upgraded form of fast Ethernet. And the last type is switched Ethernet. This Ethernet type installs network devices such as switches or hubs so as to improve the network transmission. The transmission range for switched Ethernet connection is around 1000 Mbps to 10 Gbps. Now let's look into the working of Ethernet. Ethernet services specifically work in the first layer of the OSI model, that is known as the physical layer, and the second layer of the OSI model, also known as data link layer. Functioning of the Ethernet can be divided into three different parts. First step being acquiring the physical address, that is MAC address, media access control address of the sender and the receiver device. Then the second step is to check the data security, quality of the data, and the connection speed of the transmission channel for efficient and smooth transmission of data over the network. And the last step is to check network traffic and detect any error that occurs in the communication channel. To solve these issues, if occur, CSMA protocols and other protocols are used. For example, the CSMA protocol is used in case of packet collision in the network channel. Now let's look at a simple Ethernet model for further clarification of the steps. But before we begin with the model, the point to be noted is the transmission of data over the Ethernet channel is divided into two parts, frames and packets, where packets represents a unit of data in the network, whereas frame refers to a collection of data packets being transmitted over the channel. And the application of Ethernet services, which includes security, traffic check, and protocols being applied on the data, and that is when it reaches the receiver end. Moving on, let's look into advantages and disadvantages of using Ethernet. For advantages we have, cost of installing Ethernet connection is low in comparison to other network channels. The security of the data being transmitted over the Ethernet channel is maintained. As for disadvantages we have, it is suitable only for establishing short distance communication network due to high requirement of hardware resources. Whereas Ethernet is also not suitable for sharing real-time data and information. Let's look into some more advantages and disadvantages. Ethernet is suitable for maintaining the data quality of the information being transmitted. It also provides high-speed data transmission option for the network. For disadvantages we have, the network traffic issue is a drawback of installing Ethernet cables. Troubleshooting faults and issues in the Ethernet cable is also a troublesome work. Now let's move on to the last heading for this topic, that is Ethernet versus Internet. The first difference is connection medium. For Ethernet connection, physical cables are required. That means it uses wired medium for connection. Whereas in case of Internet, it uses wireless medium such as satellites as a connection medium. Moving on, the next difference is network model. The Ethernet is available only for a low distance connection, for example, LAN, whereas Internet is available for all the network connection distances, be it LAN, MAN, or WAN. Let's move on to the next difference, that is network control. For Ethernet, the complexity of the connection medium is low due to the less distance it uses, and also provides much efficient transmission of data over the communication channel. Whereas for Internet is a large collection of networks and hence require large group of administrator for control. The last difference between Ethernet and Internet is network security and reliability. Ethernet connection is a secure network from external interference and provides data security, whereas in case of internet, it is an open type of connection, so it is more prone to hacking attempts and less secure network. Let's begin with the introduction to the network hub. A network hub is a device that is designed to connect multiple network units in a closely connected network channel. So hubs are also used in LAN networks. The network hub shares data with the destination device by acting as a central connection point of data transmission and connecting all the other devices in the channel. Some points to remember about the working of a hub. Hub is incapable of processing any complex protocols due to the absence of an intelligent unit in the system. Also, the physical model of the hub is composed of multiple sockets for connecting network devices. Now let's move on to the working of a network hub. For the first scenario, we will assume that a message is being sent through the hub to a destination node. Let's begin. According to the example, hub has received a message for device A, where it will share the same message to device A, which is a basic protocol. But due to the absence of any intelligent unit or a processing point in the hub device, it will share the message for A to all the other connected devices that are device B as well as device C. This creates a lot of access of traffic in the network channel. Now let's move on to the second scenario, which is when receiving a response from the device. In this case, when the device A shares a response to the hub to be sent to the sender device, it will share the same response to all the other connected devices, again due to the same reason, that is lack of any processing unit or intelligent point in the network channel. Please take a look at the arrow points, which is very important during the transmission of data. With this, we have cleared all the points that are important for a network hub. Now let's move on to the next topic, that is information on switches. The network switch is a networking device that is active in the data link layer of the OSI model and is designed specifically to connect private networks in a LAN channel. Switches are programmed to share messages only with a designated device that is mentioned in the header format of the message, which cuts down the network traffic in the channel. Switches uses different types of data, which can be either packets or data frames. Switch uses a destination source address and the destination address for forwarding the message to the specific device in the system. Now let's look into the working of a network switch. The first scenario is when the message is received to a switch and is to be forwarded to a particular device. In this case, we are receiving a message for device A, which will be shared only to device A according to the address mentioned in the header format. This decreases the network traffic in the channel and also prevent the access of message to device B and device C. This task of managing the address and sending the data to the designated device is handled using MAC address, which is used by the network card installed in the network device. Now let's move on to the second scenario, that is receiving a response from the device. In this case, the switch will receive a response from device A, which will be forwarded to the sender's address mentioned in the message. And this will prevent the response to be shared to device B and device C due to the presence of a processing unit in the switch. With this, we have completed all the important points to be known regarding a network switch. Now let's move on to the third topic, that is information on routers. Let's begin. A network router is a device that is designed to share data between multiple networks at a much larger scale in comparison to a hub or a network switch. It is connected to multiple devices at a very large level that can be considered as metropolitan area network or a wide area network. Router uses IP addresses to share data with the specified device in the network channel. And they also perform the task of translating an address that is available in a private network to a globally recognized network so that it can access internet, which is known as NAT, Network Address Translation. If you want to look further in the translation process that the router performs, you can visit our video on the same in the Simplilearn channel. Now, with this we have completed all the introduction points regarding a network router. Now let's move on to the working of a network router. In this scenario, a message has been received by the router for device A, from which it will deduce the IP address for the device A and share the data. The message deliver efficiency is highest in case of a network router as it uses routing path from a routing table to guide the message to its destination point and vice versa. With this, we have completed all the important points regarding a network router. Now let's move on to the last heading for this session, that is difference between a network hub, switch and a router. For this difference, we will use different features to differentiate the working of a hub, switch and a router. The first difference is based upon the OSI model layer. In case of a hub, it is active in the physical layer of the OSI model, that is also known as the first layer. And in case of a switch, it is active in the data link layer of the OSI model, also known as the second layer. Whereas a network router is active in the network layer of the OSI model, also known as the third layer. Now let's move on to the next difference, that is based on addresses used by each of them. Let's take a look. A hub, as we already discussed, doesn't use a MAC address or an IP address for the transmission of data in the network channel. In case of a switch, it uses MAC addresses available in the network channel to provide a guidance system for the message to be transferred. Whereas in case of a router, it uses IP addresses to transmit the data to the designated device. Let's move on to some other differences, that is, format of data used in each of them. Hub uses electrical signals or bits for data transmission in a network channel, whereas switch uses a data frame or data packets for the transmission of data over the communication channel. And in case of a router, it uses data packets to be transferred. And the next difference is based on the mode of transmission. Let's take a look for this. A hub is based on half duplex network connection. That means at a certain point of time, only a single device can share or receive data from the other endpoint of the network channel. And in case of a switch, it is full duplex network connection. That means it can simultaneously receive and send a data packet or a data frame to any of the network devices connected in the system. Similarly, a router is also based upon the full duplex network connection form. Let's move on to the next difference, that is installation purpose. On the basis of installation purpose, a hub is mainly preferred in a LAN network or in a private network where 2 to 3 devices are to be connected, which increases the efficiency due to the absence of a processing unit in a hub. As for a switch, it connects multiple LAN networks or a large area network available. As for the case in a Network router. It is a global network that connects multiple devices across the globe and is also designed to connect internet to any of the device. Let's take a look at the next difference. That is device classification. In case of a hub, it uses broadcast format or a broadcasting device to transmit data over the communication channel due to the absence of any processing unit in the system. And in case of a switch, it uses multicasting application for the transmission of data. And in case of a router, it uses routing path from a routing table to transmit the data in the communication channel. Let's take a look at a few more differences. That is installation cost. A network hub can be installed very easily in a network channel as it does not perform any complex task. In case of a switch, it required moderate cost installation as it performs some complex queries or complex protocols in the network channel. Whereas in case of a router, it is the most expensive to install in the network channel due to the high device specs and the performance based protocol. And the next difference is based upon processing and intelligence. Now that we are clear, a hub device does not have any processing unit or intelligence point and is the most basic point of data transmission. Whereas in case of a switch, it possesses a processing unit to differentiate the destination address or a source address in the header format of the message. Whereas in case of a network router, it is the most sophisticated device among all the three network devices as it performs the most complex queries and protocols in the network channel.
What is network topology? It is referred to as an arrangement of multiple systems and network devices interconnected to each other through a physical medium or logical channel. The term network topology is a combination of two individual network concepts. First is the network part, which represents the devices or systems that are also known as nodes, which is connected and how to change the data within the network. Then the other part is topology, which represents the connection medium between different network devices and governs the data flow between them. Moving on, let's talk about why do we apply the concept of network topology. For the first point, it allows the users to understand the overall model of the network along with the number of devices installed and their positions in the network, which provide ease of installation of security measures and network and helps in case of troubleshooting cases. Then, for the next reason, applying network topology helps the user to understand the communication relationship among the different devices and through a connection medium. This in turn helps the network professionals to set up an optimal network unit for the user. Next in the list, we have different types of topologies used in networking. First is the bus topology, then we have ring topology, then star topology, then tree topology, and in the end, mesh topology. But to understand the concept of topology, let's start by point-to-point topology. This is simplest form of topology connection which consists of two nodes connected through a connection medium like a network cable. The nodes at the two ends of the cable shares data information between them, where the data sharing part represents the network and the cable connection is the topology part. With this, we have understanding of network topology. Then let's begin with complex types of tech connections. First is the bus topology. In this topology, the connection channel is a single cable known as the network backbone, through which all the other nodes are connected to. In this network setting, the data packets sent by the nodes are provided with the receiver address to avoid transmission errors. The data in this topology can travel from any endpoint where they are termed as terminate points. Advantages of bus topology. It is easy to set up due to the simple configuration settings. This setting is also cost effective as it requires only a network cable for the connection. In the case of crash node, the whole network remains unaffected as it does not have any direct connection to the other node. Let's take a look at disadvantages of bus topology. In case of troubleshooting, we require the use of special equipment to detect the fault in the network. In the case of multiple data transmission, the packet collision is the frequent occurrence, damaging the transmitted message data due to the unavailability of network devices such as switches, repeaters, etc. The loss of data over long distances communication is quite high. Then ring topology. As the name suggests, the nodes in the network are connected in a circular pattern similar to a ring. The data transmitted in this connection is always in the clockwise direction. The topology does not have any termination point due to its ring structure. The method of data transmission is known as token passing, which involves sending a token along with the data packet to which each of the node matches to identify the destination node using the destination address in the token. Next, advantages of ring topology. The crash node can be easily removed from the network. The configuration settings are not complex for setup, and materials are easily accessible. The cost of installation is low as no extra network devices are required to the connection. Moving on, we have disadvantages of ring topology. In the case of a node crash, the whole system is affected and is non-accessible due to the direct connection of each node. The transfer of data is slow due to the token passing method in the network. Difficulty in the troubleshooting fault in the connection leads to the crash of the whole network. Now let's talk about star topology. In this topology, the networks are connected to each other through the central hub, which can be a computer or a server. The central unit in the connection is also known as the server, and the nodes are known as the clients. Any connection between the nodes has to be through the server and is one of the most popular topology connections. Next, advantages of star topology. In case of a node crash, the network as a whole remains unaffected as each node is connected to the server of a connection. The hardware requirements are easily available and of low cost. Troubleshooting is easy through the use of central hub to identify the faulty node. Disadvantages. In case of a server failure, the whole network is shut down as all nodes are interconnected through the server. The connection configuration is complex due to the pattern of the topology. Next up, tree topology. This topology is a combination of star and bus topology. The node connection in the topology follows hierarchical pattern, with the topmost node as the root and the branching nodes as the child node. The sharing of data is from the root node to the child node pattern. Next up, advantages of tree. Installation of a new network group is easy due to the root-child configuration of the network. In case of a node fault or crash, the whole network is not affected by the error. This makes it easier to troubleshoot the issue. Next up, disadvantages. In case of a server crash in any of the star connection groups, the whole network is affected. Due to the complex setting of the topology, installing security points is difficult in the network. Configuring and troubleshooting internal issues is quite complex due to this topology. Next up, mesh topology. As the name suggests, this topology is a connection of interconnected systems connected to each other in no particular order. No installation of network devices such as switch or hubs. This topology pattern can be divided into two forms. First is full mesh topology. In this connection, all the nodes are connected to each other in the network. Then we have partial mesh topology, where all of the nodes are connected to each other available in the network. Let's talk about the advantages of mesh topology. In case of a node damage, the whole network does not suffer from the fault. Due to the interconnected patterns of the connection, the transmission of data is very high in the network. Next up, disadvantages. The cost of installation is high due to the requirement of multiple cables and nodes for the network to function efficiently. The management of the network becomes complex due to the large number of interconnections in the network. Due to the absence of repeater or a switch, the data signal loss during the transmission is very high. Now, let's take a look at how to choose best topology for a network configuration. First up, cost. The installation cost is one of the biggest factors that affects the type of topology configuration we choose from our network, as the cost of installing cables, routers, switches, and other network connections is low. Then we have easy installation. Installing the hardware devices efficiently and precisely is also one of the factors that affect our choice of network topology. Moving on, we have flexibility. The ability of the topology to include new network nodes after installation and ease of troubleshooting refers to the flexibility of topology. In the hand, we have reliable security. It is important that the topology installed allows us to introduce proper security points in the network and leading to fewer crash cases. By referring the above factors, we can decide the best topology for our network.
Firstly, we'll understand what exactly is the model. The TCP/IP model is a method of sharing data and information over the communication channel, where the data has to go through each of the four-layer structure of the network model, where it also performs tasks such as remodeling of data, efficient transmission, and error-related issues. Each layer has dedicated protocols that they enact on the transmission data. Now let's continue with the protocols that are used in the TCP/IP model. To understand the protocols that are used in the TCP/IP model, we'll compare it with the OSI model. And if you want to know more about the OSI model, you can visit our video on the Simplilearn channel. Let's begin. The topmost three layers of the OSI model, which are application layer, presentation layer, and session layer, collectively refers to the application layer in the TCP/IP model, where they use protocols such as FTP File Transfer Protocol, HTTP Hypertext Transfer Protocol, Telnet, and SMTP, which is Simple Mail Transfer Protocol. Then we have the transport layer from OSI model, which refers to the transport layer in the TCP/IP model, where they apply protocols such as TCP, Transmission Control Protocol, and UDP, User Datagram Protocol. Moving on, we have network layer from the OSI model, which refers to the internet layer in the TCP/IP model, which apply protocols such as IP, Internet Protocol, ICMP, Internet Control Message Protocol, and ARP, Address Resolution Protocol. Then we have data link layer and physical layer from the OSI model, which refer to the network access layer in the TCP/IP model. These layer doesn't exactly apply any protocol but are connected through physical medium, which includes Ethernet, Wi-Fi, and cables. Now that we are completed with the protocols regarding TCP/IP model, let's take a look at the layers in detail. The TCP/IP network model consists of different layers, where the original model consists of four different layers, which are application layer, transport layer, internet layer, and network access layer. Then we have the updated model, which consists of layer, application layer, transport layer, internet layer, data link layer, and physical layer. Let's take a look at the layers in detail. The first layer that we are going to know about is the application layer. Application layer. This layer acts as an interface between the application and programs that require the TCP/IP model for communication, including tasks performed by the layer, such as data representation for the software application that are executed by the user, and then forwarded to the transport layer. The protocols supplied by this layers are HTTP, Hypertext Transfer Protocol, which is used to access information available on the internet. Then we have SMTP, Simple Mail Transfer Protocol, which is used to access email-related tasks. Moving forward, we have the transport layer. This layer is responsible for establishing connection between the sender and the receiver device. This layer performs the task of dividing the data from the application layer into packets, where they are used to create sequences, which are then transferred over to the destination device. It also performs the task of maintaining the data, that is, to be transmitted without error, and controls the data flow rate. The protocols that are applied in the transport layer are TCP, Transmission Control Protocol, which is responsible for transmission of segments over the communication channel. Then we have UDP, User Datagram Protocol, which is responsible for identifying error in the data that is to be transmitted over the communication channel. Moving forward, the next layer is the Internet layer. This layer is responsible for the transmission of data over the network channel. That is, they provide a proper route for the packets to be transferred over the communication channel. The protocols that are applied by this internet layer are IP protocol, which is the internet protocol. This protocol assigns a unique address to a physical system so that it can be identified on the internet. Then we have ARP, Address Resolution Protocol. This protocol is used to find the physical address of the system using the Internet Protocol address. In the end, we have the Network Access Layer. This layer is a combination of data link layer and physical layer from the OSI model, where it is responsible for maintaining the task of sending and receiving data in raw bits. The raw bits are transferred from the sender side to the receiver side in the format of binary digit, which are zeros and ones. Let's move on with the advantages of using the TCP/IP model. The TCP/IP model assigns an IP address to each of the system that is available on the network channel so that they can be identified on the internet. Then they are also responsible for enacting different protocols on the data that is to be transmitted over the communication channel. The TCP/IP model also enables the user and the system to access different format of data over the communication channel. Now let's take a look at the last topic for this session, which is the OSI model versus the TCP/IP model. On comparing both of the network models, we get the OSI model consists of 7 different layers, whereas the TCP/IP model comprises of 4 different layers. The OSI model has separate session layer, presentation layer, whereas the TCP/IP model comprises of a single application layer. The transport layer in the OSI model provides packet delivery protocols, but in the TCP/IP model, transport layer does not provide any such protocols. The OSI model is implemented during network communication, but in case of TCP/IP model, it is used as a reference model for the network channel. To better understand the OSI model, let's take a look at a scenario. Assuming we have two different systems with different operating system installed in them, and there is a communication channel between them over which the data is shared. But sometimes during transmission of data, it faces some problems. These errors often arise due to the different operating system installed in the system or due to a network problem during a transmission. But to overcome such situations, the OSI model structure is used. Using the OSI model structure, we can make the transmission of data over the communication channel error-free. Let's take a look at the definition for the OSI model. The OSI model stands for Open System Interconnection Model, or a specifically designed set of protocols and standards that governs the modeling and conversion of the data for proper transmission over the network channels. The OSI model is based on the layer structure, where it consists of 7 different layers, where each layer has different set of protocols that are to be applied on the data during the transmission over the network channel. Let's take a look at the different layers of the OSI model. The OSI model consists of 7 different layers which perform specific functions and apply different protocols at different layers to maintain the quality and prevent the data from getting corrupted when it is transmitted over the communication channel. Let's take a look at each of them. The first layer is known as the application layer, which is the topmost layer. Then we have the presentation layer, session layer, transport layer, network layer, data link layer, and physical layer, which is the last layer of the OSI model. The upper 4 layers in the OSI model represents the host layers. That is, they interact with the application related issues when the data is transmitted over the communication channel, whereas the lower layers are termed as network layers. They specifically deal with the transmission related steps for the data over the network channel. Let's take a look about some information in regards to the layers. Now let's take a look at the function and the data format that is handled by each of the layers during the transmission of data. The first layer is the application layer, which interacts as a gateway for the host data and network applications and handles the data format. Then we have the presentation layer, which handles the initial step towards the conversation of data for transfer. It also handles the data format. Then we have the session layer. Session layer establishes a connection between the network devices for the data transfer. Then we have the transport layer, which oversees the data that is transferred without any error and is in the same pattern needed by the destination system. The data format handled by this layer is segment format. Next, we have the network layer, which determines the path for the data transfer. It handles packet related data. Then we have the data link layer, which performs the task of connecting the physical nodes for the transfer of data. It handles frame data. And in the end, we have the physical layer, which is used to transfer the raw bits, that is, in terms of ones and zeros, over the physical mode. Now that we are clear about different layers that are present in the OSI model and some information regarding them, let's take a look at each of the layers in detail. We'll start with top to bottom. That is, the application layer will be the layer that we'll be starting with. Let's take a look. The topmost layer in the OSI model is the application layer, which acts as an interface between the user and the applications that are being accessed, which can be Internet Explorer, Chrome, or any email client. It also handles different protocols that are needed for the data transmission over the network channel, which can be given as Hypertext Transfer Protocol, the HTTP protocol, and the SMTP protocol, which is the Simple Mail Transfer Protocols. Now let's move on to the next layer. The next layer is known as the presentation layer. The presentation layer is responsible for performing conversion tasks over the data that is received from the application layer. The conversion of data is done in accordance to the required format. It also performs encryption over the converted data so as to prevent it from getting hacked by cybercriminals or hackers. The compression of the encrypted data is also performed by the presentation layer so that it can be passed on to the session layer. The next layer in the OSI model is known as the session layer. In this layer, the communication channel between two different devices is established. The network devices are individually known as session. The data that is transferred is to be done over these session channels. The layer that is the session layer establishes and terminates these sessions in case of an error or some other unforeseen event. This layer is also responsible for authentication checks regarding the data that is being transferred and also provides data recovery options in case an error occurs over the communication channel. OSI model layers, let's take up a question. The question is, what is the main action that takes place at the presentation layer? And the options are: first option, data segmentation; second option, encryption of data; third option, framing of data; and the fourth option, bit conversion of data. You can provide your answers in the comment section below. Let's move on with the next layer. The next layer in the OSI model is known as the transport layer. The main task performed by this layer is to break the data that is received from the session layer into different segments. These segments comprises of protocols which are UDP protocol and TCP protocol along with the data that is segmented from the received data. Then the segmented data along with the UDP and TCP identification is transferred over to the transmission channel, where then it's further transferred to the network devices that requested for the data. This layer also performs a very crucial part, which is the flow control. Let's understand flow control over the network channel through a small example. In this example, the server has a capacity to send 50 Mbps of data at once, whereas the receiver side has a capacity for 10 Mbps. When the data is transferred from the server to the client, it transfers 50 Mbps. But it isn't possible to transfer all this data at once due to the lower capacity on the client side, which is why the flow control changes is required, which is provided to the server side by the transport layer. Now let's move on to the network layer, which is the third layer from the bottom in the OSI model. This layer is responsible for breaking down the segments into data packets by adding IP address to them that is received from the transport layer. These data packets are then further transmitted over through the best possible route to the destination system, which are governed by the Internet protocols, including IP and IPv6 protocols. For example, if we have a data that is to be transferred to the network device 2, we choose the best option, that is the route to be transferred over to that network device. Now let's move on to the next layer in the OSI model, which is a data link layer. This layer is responsible for maintaining and terminating the established connection between the devices over the network. The MAC address in this layer is added to the data packets, which are collectively known as data frames. These data frames are then further transmitted over to the physical network. These are divided into two different sublayers. Medium access control, that is MAC, which controls the established connection device. And the second sublayer is logical link control layer, LLC, which identifies the address and provides flow control for the data. This data frame, as earlier told, is transferred over to the physical layer. Now let's take a look at another question to brush up whatever we learned so far. The question is, which layer includes the MAC sublayer in the OSI model? Option 1, application layer; option 2, session layer; option 3, data link layer; option 4, transport layer. You can give your answers in the comment section below. Let's move on to the last layer in the OSI model, which is a physical layer. This layer is responsible and provides the physical medium over which the data frame is transferred. But the transfer data is converted into bits before it's transferred. The transmission of data is covered by different protocols that are embedded in the physical layer. The transmission of ones and zeros format data is done. It also responsible for maintaining the data quality by applying different necessary protocols and maintaining the bit rate throughout the transfer of data, whether it be wired medium or wireless medium. Let's understand the DHCP protocol. The Dynamic Host Protocol, or DHCP, is a protocol that is designed to assign the IP address to a device for it to access the internet. This network model is based on the client-server architecture and removes the process of manually assigning an IP address to the system. Now let's take a look at the allocation methods for the DHCP protocol. The allocation method of DHCP is divided into two types. The first type is the manual allocation, which, as the name suggests, is the assigning of IP address to the system manually by the user. The second method is dynamic allocation, which uses a client-server architecture to assign an IP address to the system. Now let's see some points regarding the allocation method. The first type is the manual allocation. As mentioned, in this allocation type, the user manually assigns the IP address to the system for accessing the internet and can be observed in this instance. This is done by accessing the network configuration setting of the device and also requires other related configurations such as subnet mask, preferred DNS server, and default gateway. Let's now take a look at the dynamic allocation. In this allocation method, the client device receives all the relevant network configurations from the DHCP server, and the system gets configured to access the internet. The provided IP address is given for a certain period, which is also termed as the lease. Now that we somewhat understand what exactly the dynamic allocation in DHCP server is, let's take a look at a small example. Open the Start menu and type command prompt. When the windows open up, type ipconfig/all command. As we see, by this command we can take a look at the network settings for our system. Over here we can see the DHCP is enabled. That means the configuration that has been used on the system refers to the DHCP server. And on the bottom side we can take a look at the different network settings that are given along with the IP address by the DHCP server. That is subnet mask, default gateway, and the DNS server. Now let's continue with the video. Now let's take a look at some of the notable DHCP settings. The first one is known as scope. As the name suggests, a scope refers to a range of addresses that are available to a DHCP server for allocation of the client device. Next we have is lease. This setting of the DHCP server is designed to prevent the hoarding of IP addresses by a single device. This is done by assigning an expiration date to the leased IP address so that the DHCP server has some minimum addresses left for the client device. And lastly, we have address reservation. In this DHCP setting, the client device requests the server to assign the same IP address to the device each time the address allocation takes place. This is done by identifying the MAC address of the client device. Now let's take a look at the operation model for DHCP protocol. The DHCP operations are performed under User Datagram Protocol, in short UDP, which is applied on two ports under UDP, which are ports 67 and 68. The first phase is where the client broadcasts a DHCP server message over the network to connect with the DHCP server. This message basically means that it wants to connect to the internet through the DHCP server. The second phase is when the DHCP server receives the DHCP message. According to the message, the DHCP server reserves an IP address for the client and network configuration information, including subnet mask, default gateway, and preferred DNS server. In the third phase, the client responds to the DHCP server's offer through a DHCP request message, requesting the offered IP address and relevant network configuration for the system. Then in the last phase, the server acknowledges the request broadcast from the client and sends the DHCP packet to the DHCP client, which is comprised of network configuration for the client device. What is network address translation? The motive behind implementing NAT is to allow several network devices to connect to the internet by a single public address. The NAT model is a method to conserve IP addresses by using a unique address to represent the whole private network. And the mentioned public IP address is a globally recognized IP address to access the internet. Let's move on to some more details regarding network address translation. The task of NAT process is to translate a private IP address in a network to a globally recognized public IP address and vice versa. That is, the same process begins from public IP address to a private IP address. This task is performed by a router or a NAT firewall. Let's move on. The flow of this process is something similar, like the router configured acts as an interface between the private network and the public network. That means the private network will communicate with the router when it wants to access an internet. Same is the case for public addresses too. When the public address wants to communicate with the private network, the router will convert it to a private network ID and allow us to access the internet. The reason behind applying NAT process is to conserve public IP addresses. To be more specific, it's IPv4 addresses, and it also provides much better security to the network. Now let's move on to the next topic, NAT addresses. There are different types of terms used in NAT process. More specifically, there are some addresses information that are necessary to understand the process which takes place during network translation. We will discuss them one by one. Let's take a look at the first address. Before we begin, let's take a look at the example. This is a general or a simple form of NAT translation process. We have a private network, a private device, a router, a public network that we can access internet through. The first term that is used is known as inside local address. This IP address represents the host of the private network, and this cannot access the internet directly unless provided by an ISP server. After we have the inside local address, through the private network, we share it with the router. When the router receives this private network ID, it converts it to the public network. That is known as inside global address. This IP address represents the whole private network for the outside network and is used to access the internet for the private network. Now let's move on to the remaining IP addresses for NAT. According to this example, now we are returning from a public network to the private network. Please keep that in mind. According to this, the address type next comes up as outside global address. This IP address represents the outside network address for the host before NAT process took place. Then we have outside local address. This IP address represents the actual address representing the host on the internet after the NAT process takes place. Now let's move on to the next heading in the topic.
Choose from over 300 in-demand skills and get access to 1,000 plus hours of video content for free. Visit SkillUp by Simplilearn. Click on the link in the description to know more.
Types of NAT. There are different types of NAT available on the internet or in the network channel, but we will discuss three generally used ones, where the first one is known as static NAT. According to static NAT process, in the given private network, each device will have a particular or a single IP address publicly designed to them. That means if you have two devices in your private network, you'll have two different types of public IP addresses for each of those IP addresses that is available in your private network. Due to this property of the static NAT process, it is also known as one-to-one NAT and is mostly used for personal addresses. For example, please take a look at the diagram below. If we have a single IP address in a private network, we will have a single public IP address for the same. Again, if we have another private IP address in the private network, we will have a public IP address for the same. This represents static network. Let's move on to the next one. The next type of NAT process is known as dynamic NAT. For the dynamic NAT process, private network addresses is translated to public addresses from a pool of public IP addresses available to the communication channel. That is something similar to this. According to the example, if we have two private addresses available in the network, then we have two pool of public addresses too, out of which we can convert the private address to a public address. And for example, if we have a third private address and only two possible public addresses pool, then the third address is dropped. Let's take a look at the diagram for a clarification. This is the pool of public addresses available for this network, out of which we converted 192.168.32.10 to 213.18.123 to 0.100. Now let's move on to the last type of NAT available. This NAT is known as port address translation. In port address translation of NAT, the process takes place something similar like this. All the available private IP addresses in the private network are converted to a single available IP address publicly recognized. That means if you have 5 private networks in your available network, you will have a single public IP address available to all of them. Due to this nature of this process, it is also known as NAT overload. But the catch is, all the addresses in the private network available will have different port number assigned to differentiate between them. For example, 192.168.32.10 is translated to 213.18.123.100.11, where 101 represents the port number. Similarly, for the second private network, we have 192.168.32.12, which translates to 213.18.123.100, that is similar with the earlier case. But the change comes over 0.102, that is the port number assigned to the second private address. Now let's take up a small quiz to refresh all the topics that we read so far. And the first question is, what does outside local address refer to in NAT? Your options are name of inside source address before translation, name of destination host before translation, name of inside host after translation, name of outside destination host after translation. Please read the options very carefully to answer this. Now let's move on to the next question. And the question is, PAT address is also termed as. PAT refers to port address translation. Option A, static NAT. Option B, one-to-one NAT. Option C, NAT overload. And option D, NAT overlapping. You can give your answers in the comment section. Now let's move on to the last heading for this session, that is advantages and disadvantages of applying NAT in a network channel. Let's take a look at the first advantage of using NAT. NAT provides privacy and security measures to the private address as it converts the private address to a public address, through which we can prevent our ID from being hacked over the internet. Let's move on to the next advantage. NAT process is applied to conserve approved IP addresses over the network channel. As discussed earlier in the previous slides, NAT process helps to conserve us IPv4 addresses. Now let's look into some disadvantages of applying NAT in the network channel. And the first disadvantage is NAT translation leads to path delay and prevents some applications to lose their access over the network channel. Now let's take a look at the second disadvantage. According to the NAT process, router is the one that translates a private address to a public address or vice versa. During this process, it does happen to tamper with the port numbers, as we already discussed. But according to the rules set by the network channel, router is not usually allowed to hamper with the port numbers, but it has to because of NAT. Introduction to distance vector routing. Distance vector routing refers to the distance or the vector that is between the neighboring nodes in a network channel, and the routing part refers to the established route through which data packets are transmitted in the network channel. The other aspect of this routing protocol in a network channel is to determine the shortest path for a data packet in the network to reach its destination. Next, we will look into some key points regarding the routing protocol. For routing protocol, three primary key points are to be remembered. First one being, each router in this protocol is designed to share the vector data of each node throughout the network. This step is done to maintain proper circulation of data in the network channel. The next key point is the routing pattern in the network protocol. That is, the data shared by the routers is transmitted only to those nodes that are directly linked to a particular router. The last key point is that the routing protocol is designed in a manner that it shares the updated vector data periodically at the network channel. Now let's move on to the next heading, that is the algorithm used in the protocol. The algorithm used in this protocol is termed as Bellman-Fold algorithm. This algorithm defines the shortest path that a data packet can take to reach its destination node from an initial node, where d of xy refers to the least distance from a node x to node y. Moving on, we have c of x comma v, where excess cost from each of its neighboring v node is taken into consideration. Then we have d of vy. This is the distance of each neighbor from its initial node. And lastly, min of v. This is an abbreviation we use to determine the most shortest vector after the solution is obtained using the algorithm. In the next heading, that is network example, we will understand all the points used in the algorithm. Now let's design a network model with 5 different nodes that are A, B, C, and D, with each node connected to each other using different network channels. The numerical values in the network channel refers to the vector count, that is the distance from node A to node B or to some other node in the network channel. In a network model, each node shares its vector data with its neighboring node at a regular interval, as there are various updates in the network model. This data is shared in a form of routing table, where three different columns are used. First being destination column, second vector column, that is the distance node, and lastly the hop. Let's take a look at the neighboring nodes for this model. For node A, we have B and E, as it is directly interlinked to the node A. For node B, we have node A and node C. For node C, we have B and D. For D, we have C and E. And lastly, for E, we have node A and node D. These nodes represent only the neighboring nodes. Now let's solve an actual example on routing protocol to clear all our doubts and understand the key points. The example we will be taking to solve is this network model. The initial step to start solving the network model using the distance vector routing protocol is to make routing table for each of the nodes. Let's make the routing table for node A. This is the routing table for node A, where we have destination as A. That means destination is A from node A. That means the distance vector should be 0. Then we have destination as B. Let's take a look. In this given example, there is no given connection between A and B. That means this distance vector would be infinity. Then we have destination as C. Similarly as node B, there is no direct connection between A and node C. That means this is also infinity. And same is the case with node D. And in the end, we have node E, that is the only directly linked node to node A. That means the distance given is 5. So the network vector is 5. Let's make another routing table for node E. This is the routing table for node E. Let's take a look. In this routing table, the first is destination to node A. According to the network model given, distance is 5. So the vector value is 5 with the hop to A. Then we have destination as node B. According to the model, the distance vector should be 4. Then we have destination as node C. As given, there is no direct connection between node E and node C. That determines the value would be infinity. Then we have node D, which represents direct connection with node E, and the value is 7. And lastly, E destination from initial point E would be 0 vector. Now let's make another routing table similarly for node C. Now using the same steps, you can make the routing table for the remaining nodes, that is node B and node D. Now let's move on to the next step in solving the routing issue. This step is known as update step. In this step, we use the vector column from each of the node to update the vector column or the routing table for a particular node. In this part, we'll use node E's vector column to update the routing table for node A. And the steps are using the algorithm, that is the Bellman-Ford algorithm we used earlier. As we already know, moving from A to destination node A is always 0. So we won't be doing this step. Let's move on to the next one, that is moving from node A to node B. That would be A comma E, as we are using vector column of node E plus and the distance used to reach E from B. A comma E represents 5 and E to B represents 4 according to the network model. So the value is 9. Similarly, let's solve for A to C. To A to C we have A comma E plus destination required to move from E to C. According to the network model we have, node A is only directly linked with node E, so the value would be 5. But there is no connection between node E and node C, so the value would be infinity. Moving on, we have A to D. In this case, we have A comma E. The value would be 5 plus E to D, that is a direct connection, and the value would be 7. So the total distance is 12. And the last one is A to E. For this we have A comma E, that is directly the neighboring node. The value would be 5. So the new routing table for node A is 0, 9, infinity, 12 and 5. Similarly, let's take another node for this. For the next node, we will take node C and we will update the routing table of node C using its neighboring nodes, that are node B and node D according to the network model. Now, how to do this step? Firstly, it's C to destination A. In case of node B, we have C to A, that would be C comma B, that is a direct connection, plus distance required from B to A. According to the network model, we have C comma B as 6 plus B to A does not have any connection, that is infinity. So the value would be null. Then we have node D. In this case, we have C comma D, that is a direct connection, 3 plus D to A, that is again infinity, as it is not linked directly to node A. Moving on, we have destination as B. For node B, we have direct connection, so C comma B value is 6. Whereas for node D, we have C comma D, that is distance 3 plus D to B, that is infinity, as it is not directly linked with the node B. So again the value is null. Then we have destination as C. So connection between C to C is 0. Moving on, we have destination at node D. That would be C to D, as C to D, as there is no direct connection between node B and node D. So the value is infinity. Whereas for C to D is a direct connection for node D. So the value would be 3. Now for the last node, that is node E. In case of node B, we have C comma B plus B to E, where the value for C to B node is 6 and B to E is 4. So the sum is 10. And now in case of node D, we have 3 plus 7. That would be distance from C to D and then D to E. And the value would be again 10. So we can use any of the side to reach the destination node E. By completing all the steps, we have the new table for node C. Similarly, we can find the routing table for all the nodes present. Now, to look into some key points we learned. For the initial step, use only the node distance of immediate neighbors. Nodes without distance that is directly linked to each other is always infinity. For the update step, use the vector table of the only neighboring node we have for the initial node. And lastly, to continue the update step, roughly n-1 iterations are used, where the value of n is equal to the number of nodes. For example, the model we took had 5 nodes. That means we have to do a loop of 4 iterations. Assuming that a person had to send a letter to a relative's house, but he wasn't sure which house though. So, how can this problem exactly be solved? Well, this problem can be solved if we take a look at the house number mentioned on the mail. Let's take a look at the house number mentioned on the mail. On the mail, it seems like the house number is 2. That means the mail would go to house number 2. Similarly, we also have an identification method on the internet that is known as IP address, which is used to identify different mails and the owner of that email address. Firstly, we'll understand what exactly is an IP address. An IP address or Internet Protocol address, for an example, is a unique numerical identifier assigned to every network device when it connects to the Internet. This address is assigned by the Internet Service Provider, which acts as a way for the system to access the Internet applications and a unique identity for the device. Moving forward, we'll understand what exactly are IP functions. To begin with, IP functions can be divided into two types. For the first function we have, the Internet Service Provider assigns an IP address to the network device. The first function of the address is to provide an identity to the host on the Internet, whereas the second identity is used as a location address for the host on the Internet. Let's now take a look at different versions of IP address. IP addresses can be divided into two types, where the first type is known as IPv4 address, whereas the other address is known as IPv6. Let's take a look at both of them in detail. For first one we have IPv4 address. This is the original version of an IP address developed on 32-bit binary format which contains 2 to the power 32 address. The address range from 0 to 255 in terms of zeros and ones, with 4 octets, each of them separated by a period. The network device uses binary format, whereas the numerical format is used for the host reference. The first part denotes the network part in an IP address, and the second part is for the host part. Now let's move on to the IPv6 address type. With the rise in technology, the IPv4 could not complete the requirements. So the need for IPv4 arose based on 128-bit address size, which is sufficient for a long time, which is approximately 320 undecillion. This type of IPv6 address is designed for 4 hexadecimal digits and 8 sets, with each block containing 16 bits separated by a colon. Now let's take a look at the IP classes. IP classes are designed for the purpose of easy assignment of addresses to the network. Divided on the basis of class size, we have 5 classes depending upon the requirement of the network. Class A were designed to accommodate networks with a large number of network hosts, where the first bit in the octet is always 0, with the large number ranging from 0 to 127. Then we have Class B. Class B fulfill the requirements for medium-sized network hosts, where the first two bits for the network ID is 1 and 0, with a range from 128 to 191. Then we have Class C, which can fulfill the requirement for small-sized network hosts, where the first three bits for network ID is 1, 1 and 0, ranging from 192 to 223. From this, we get that class A, B and C are used for assigning addresses to the host network. And then we have class D, which is used for multicasting, which means it is used to send a signal from one host to multiple hosts, like used in video streaming, where the first 4 bits for network ID is 1, 1, 1 and 0, with a range from 124 to 239. And lastly, we have Class E. Network ID for this range is reserved for research purpose and not assigned to any network with a range from 240 to 255. Let's see different types of IP addresses. On the basis of accessibility, we have private IP addresses and public IP addresses. For private IP addresses, the devices are assigned addresses in a network and each system is provided with a unique IP address, which they can communicate through within the same network and cannot access public network. And they do provide much more security in regards to the public IP addresses. Let's take a look at the public IP address now. For public IP addresses, ISP or Internet Service Provider assigns it to the router, which allows the user to access the internet, and also different network application can be accessed with security less in comparison to private IP addresses. Let's now see the other two types of IP addresses, which are static and dynamic IP addresses. Static IP addresses is assigned manually and is constant to the system, whereas dynamic IP address is assigned by the internet service provider. For static IP addresses, the importance is much more, whereas the address is used for business and is not beneficial to have different IP each time. In case of dynamic IP address, the assigned IP for network devices do not need dedicated IP. Due to being constant in nature, static IP address is preferred to be assigned as official address for a business. Whereas in case of dynamic IP address, due to assigning different each time when it connects to the internet, address provides much better security and often prevents hacking. Now, if we want to take a look at the IP address for a system which is publicly available, we can do by the following steps. Access your internet browser and type IP address. And over here, we can take a look at the public IP address for the system. And if we want to take a look at the system IP address which is dedicated to the device, you can do the following steps. Access command prompt and write the command ipconfig, and you can take a look at the system IP address. IPv4 addresses. The first version of an IP address to be developed was based on 32-bit binary format that counts roughly around 2 to the power 32 bits of total IP addresses in IPv4 format, which was sufficient at the initial phase of network requirement, but is somewhat lacking according to the current advancement in the network technology. The addresses in this IP ranges from 0 to 225 in terms of zeros and ones, with 4 octets where each of them is separated by a period. This is an example for an IPv4 IP address, where the first 3 parts represent the network ID and the last part represents the host ID. Using the IPv4 address as our reference, we can identify IPv4 addresses from IPv6 addresses. Now let's move on to the next topic, that is IP classes. IP classes are designed to allow easy and efficient assignment of IP addresses to a network. Depending on class size, we have 5 different IP classes in a network that are named as A, B, C, and D. For the first part, we have class A that accommodates network with a large number of network hosts, where the first bit in the octet is always 0 with number value ranging from 0 to 127. Then we have class B, which can fulfill the requirement for a moderate number of network hosts. The lead bit is 1 and 0, and network ID ranges from 128 to 191. Then we have class C, which can allocate an IP address for low number of network hosts, where the first 3 bits of the network ID is 1, 1 and 0, ranging from 192 to 223. Through the above 3 classes, that is class A, B and C, we can easily identify and assign addresses to a network host. Moving on, we have class D, where it is used for multicasting. That means it is used to send multiple signals at the same time from a single host. For example, used in video streaming, where the lead bit is 111 and 0, with network ID ranges from 224 to 239. And then we have class E, where the IP bits for this is reserved for research purpose only, where the IP addresses ranges from 240 to 255. Moving on, let's take a look at some of the features for IPv4 version addresses, where the first is the memory required for storing IPv4 version addresses in a system is very low. Then we have IPv4 version addresses apply connectionless protocol for sharing data and providing the best effort in delivery. Moving on, we have stacking option for IPv4 addresses. That means in IPv4 version, it allows to create a multiple network over a single host, which allows different hosts to connect to it. Moving on, we have IPv4 version addresses being the earliest IP designed are applicable to most of the network devices and system for connecting to the internet. So it is supported by many devices. Then we have IPv6 addresses. Let's take a look. With the increase in the need for an IP address, the IPv4 version addresses are somewhat unable to complete the requirements of the network host. So the need for IPv4 version arose, which is based on a 128-bit address size, which is sufficient for a very long time. That is approximately 320 undecillion IP addresses in version 6. This type of IPv version is designed of 4 hexadecimal digit and 8 sets, with each block containing 16 bits separated by a colon. Moving on, let's take a look at some of the features for IPv6 version addresses. Where the first is IPv version 6 addresses provides an integrated security protocol for the network, that is, Internet Protocol Security, IPsec. Then we have it allows its application to extend in various services according to the need of the network. It also allows address configuration through stateful that uses DHCP server for network settings and stateless that applies auto configuration settings. IPv6 addresses also allow some methods to convert IPv4 addresses to IPv6 addresses, which is according to the requirement of the host or the network. Moving on, let's take a look at the differences between IPv4 version addresses and IPv6 version addresses. This heading would allow us to choose a best IP address that we can decide for a network. Let's take a look at the first difference, that is address and performance. In accordance to the address size, IPv4 version is composed of 32-bit address length and is the fourth version of the Internet Protocol. For IPv6, we have the address size is 128-bit long and is the latest version of the Internet Protocol. The second difference is on the basis of address field type. IPv6 addresses are based on numeric data with 4 fields, each separated by a period, whereas for IPv6 addresses are based on alphanumeric type data with 8 fields, each separated by a colon. The next difference is based on address configuration. In IPv4 version addresses, a manual setting for the network is required along with the DHCP configuration settings. Whereas in case of IPv6 version addresses, the network setting is based in accordance to the system's requirement, and it also supports auto configuration setting for the system. Moving on, we have the number of addresses in each IP. In case of IPv4, the total number of addresses are nearly 4 billion addresses, whereas in case of IPv6 version, we have 320 undecillion addresses. Now let's take up a quiz to understand what we did so far. And the question is, identify the correct form of IPv4 version address in the given options. And the options are, you can give your answers in the comment section below. Let's move on to the next difference, that is address security and functioning. IPv4 version addresses do not provide any security function for the network, whereas in case of IPv6 addresses, integrated Internet Security Protocol, that is IPsec, is responsible for the security of the network. The next difference is encryption and authentication settings. IPv4 version does not provide any encryption or authentication services for the network. IPv6 addresses do provide mandatory encryption and authentication services for its addresses. Moving on, we have address routing and performance. IPv4 version follows routing protocol, that is RIP, for network configuration and is preferred over IPv6 version. And in case of IPv6, it does not follow any routing protocols and it uses static routes for network functioning. What are switching techniques? Switching techniques are network techniques responsible for overseeing the transmission of data over different communication channels. They are also responsible for choosing the best route for data transfer. Next, we will look into why to apply these switching techniques. Using the switching techniques, we can choose the best and the most efficient route for data transfer in the network. For example, if we want to send some data from node A to node B, we can do so by moving from node A to a switch, then node D, then to node B. But doesn't this seems like too long? This is where the switching techniques plays its role. Using the switching technique, we can choose the smallest and the most efficient way, that is node A, switch, then to the node B. Next, we will look into different types of switching techniques. Switching techniques can be divided into three primary types. The first is circuit switching, that requires a predestined path for data transmission. Then we have message switching, which integrates the destination address with the data for transmission. And in the end, we have packet switching, that divides its message into smaller units known as packets. Packet switching can further be divided into two different types, that are virtual switching and datagram switching. Now let's look into some details regarding each of the types. On the first note, we have circuit switching. In circuit switching, for data transmission to occur, a pre-established path is required between the sender and the receiver node. For example, assume that we call someone. Then this request is sent over to the network switches, and a route is to be established for the signal to pass through. After that system assigns a route for the signal to pass through, then the receiver receives the call from the caller side. This is how it works. Now let's look into some points to remember about circuit switching. For circuit switching, we require a dedicated channel established between the source and the destination node for the network to pass through. The data transmission can take place only after the path is established. And the last point to remember is, other than the sender and the destination node, no node can interfere with the transmission of data to the established route. Let's look at some advantages and disadvantages of applying circuit switching in a network. For first one, we have advantages. Data transmission in circuit switching is sure to be established due to the predestined path. Circuit switching is preferred for long and continuous transmission of data due to the pre-established path route. Then let's look into some disadvantages. The time required to establish the connection is quite long due to the time required to establish a path. Also, due to the continuous transmission of data in circuit switching, more bandwidth is required for maintaining the connection. Let's move on with message switching. In message switching, no predestined path is established between the sender and the destination node in the message. This technique integrates the destination address into the data transmitted and is shared over the network. Let's look into the setup to better understand the working of message switching. For first step, the sender node integrates the destination address into the message. Then the whole message is transmitted to the switching node in the network, where it gets stored for the next transmission. And similarly, like the second step, this transmission of data is done over the whole network. And finally, through the destination address in the data, it reaches the receiver node. This is how the message switching works. Let's take a look at some points to remember about message switching. In message switching, no predestined path is established. It uses dynamic routing as the message is transmitted through the communication channel in real time. Each node in network switching stores the data unless it is transferred over to the next switch node. Let's take a look at some advantages and disadvantages of applying message switching. To begin with, let's take a look at the advantages. The size of the data that can be transmitted over message switching is variable. In message switching, the use of bandwidth is done in an efficient manner. Now let's look into some disadvantages. For message switching, the nodes that are known as the switch node is to be provided with sufficient storage memory. There is a delay in reaching the destination due to the message technique, that is, the message has to stop at each of the switch node before it is transferred over to the destination node. Now let's look into the last switching technique, that is packet switching. In packet switching, the message is broken into smaller data units known as packets. These packets are appended with relevant network details for the transmission over the network. Let's look into the working of packet switching. We know that in packet switching, the data is broken into smaller units packets, which each packet is given a sequence number for identification. These packets are integrated with required sender and receiver address and switching method to choose the smallest route to reach the destination node. These packets are then recombined at the destination node in the correct sequence order. Now let's look into some points to remember for packet switching. For packet switching, all the data packets that are provided with unique number for identification at the receiver end, that is 1, 2, 3 and 4 in the previous example we just used. Packet switching chooses the most shortest path possible for the data to reach the destination end. In case we have unreached packet or some unattained packet, the whole message from the sender side is sent again to the receiver end. Now let's look into some details regarding advantages and disadvantages of applying packet switching. Advantages of using packet switching is it provides rerouting in case the network node is busy. It also allows multiple users to access the same network and no predestined path is needed. The disadvantage of applying packet switching is the protocols that are needed for the working of packet switching is very complex. There are often cases of loss of data packets during the transmission in case of overloading or corruption of data. The first heading is what is subnetting? The process of subnetting is to divide the network into smaller network parts. This allows the system to have better connectivity in the system. It also increases the security measures for the network against hacking attempts and also maintains an efficient flow of network traffic. The smaller divided units of the network are known as subnetworks. Taking an example of an IP address with /24 representing the subnet mask can be divided into two subnetworks of /25 subnet mask, which can further be divided into smaller subnetworks. Now that we understand what is subnetting, let's move on to class addresses and subnet mask. Firstly, let's begin with class addresses. To better understand the subnetting process, we need some information regarding different classes used in IP address, where the first class is class A with a range of 0 to 127, network bits as /8. Then we have class B with a range of 128 to 191 with network bits as 16. And lastly we have class C with network range of 192 to 223 with network bits as 24. The network bits representing each class are very important when making subnets of a particular IP address. Let's see how they do so. For this, we'll be representing each class in binary format. For class A, we have 1 for 8 bits. For class B, 16 bits. And class C, 24 bits. Moving on, we will see what exactly is the subnet mask. To better define the subnetworks in the system, we require the use of a subnet mask. That is, the subnet mask is a way to differentiate between the portion of an IP address that represents the network address ID and the host network ID. In this, let's see the default subnet mask for each of the class. For class A, we have 255.0.0.0. For class B, we have 255.255.0.0. Whereas for class C, we have 255.255.255.0. To better understand this, let's take a look at the classes individually. The network ID part is the one that represents the binary digit 1, whereas host ID represents binary digit 0. That means for class A, we have 8 bits as network ID and the remaining bits as host ID. By looking at the host ID, we can see that the network addresses that are available for the host is the largest in the class A. Whereas for class B, we have 16 bits for network ID and the remaining for host ID, where we can see the remaining part for the host ID is lesser than class A. That means class B can assign network IDs for a medium level company. And lastly for class C we have 24 bits as network ID and the remaining for host ID. From this we can see that the host ID used for class C is the lowest. That means only smaller division companies can use class C. Moving on, let's take a look at the characteristics of the subnetting process. First is the network ID, which represents the first IP address in each subnet block. Then we have broadcast ID, which indicates the last IP address of the subnetwork block. Moving on, we have first host ID, which is the immediate first IP address after the network ID. Then we have last host ID. As the name suggests, it defines the IP address before the broadcast ID. Continuing, we have next network ID. This defines the network ID of the next subnet block. Then we have the total number of IP addresses in the subnetwork block. And lastly, we have subnet mask or CIDR, which represents the network ID and the host ID part in an IP address. To better understand all the attributes of the subnetting, let's take a look at an example. In this example, we are assuming an IP address 168.0.x with a subnet mask of 24. For this IP address, we have divided it into 4 parts that represent /25, /27, /27, and last part as /26. Now let's find out the details, that means the attributes for the subnetwork /25. The first attribute is the number of IP addresses. Going by the table, we have 0 to 256 addresses in a single block. But in this, /25 represent only 0 to 128. That means the total number of addresses in /25 subnet block is 128. Moving on, we'll find out subnet mask or CIDR. That is, the default subnet mask of class C, which I have taken reference from the subnet table which was explained in the earlier slide, which is 255.255.255.128. Then we have the network ID, which represents the topmost network address in the subnetwork block. In our case, it is 192.168.0.0. Then we have broadcast ID, which is the last IP address in any subnetwork block. In our case, it is 192.168.0.127. Moving on, the network ID and the broadcast ID addresses cannot be assigned to any network device in the network, because the network ID is used to identify the subnetwork block in a network, along with the broadcast ID, which is used to communicate with any of the hosts that is connected to the subnetwork block. That also means that the total number of usable network ID addresses in a network block is total number of IP addresses minus 2, that represents network ID and broadcast ID. That would be 128 minus 2, and we get the value 126, which represents the total number of IP addresses that are usable. Moving on, the next attribute is first host ID. That means the first ID after the network ID, which is 192.168.0.1. Then we have the last host ID, which is 192.168.0.126, which is just before the broadcast ID. And lastly, the next network ID, which is 192.168.0.128. Now that we are clear about all the characteristics of our subnetwork, how about a practice round for everyone to find all the characteristics for the subnetwork block /27 subnet mask? You can give your answers in the comment section. Let's move on to the benefits of using subnetting, where the first benefit is enhanced network efficiency. Through the use of applications of subnetting, we can share data to not only a specific portion of the network model, rather than broadcasting to the whole network, causing unnecessary traffic in the channel, as shown in the example. Over here, we see 4 different hosts, and if we want to share specific data to only 2 of the hosts, we can subnet them into specific parts. Through this, the router will only send data to the specific portion of a subnetwork rather than broadcasting to the whole network channel. This will prevent network traffic. Moving on, the other benefit of using subnetting process is network security. Subnetting also provides protection to an extent against any hacking attempts made on the network model, due to the complexity of the subnetworks as presented in the example. During the hacking attempt, if we can identify how the virus attacks the network model, we can prevent it from attacking all the subnetworks by compromising a single or 2 of them and preventing the remaining subnetworks. Let's move on to the drawbacks of using subnetting process. The very first drawback of using the subnetting process is it makes the network model much more complex, which in turn affects the maintenance and efficiency. Then we have the unused IP addresses which are left over from applying the network model in a subnetwork process. And lastly, we have the low efficiency use of hardware devices. If the hardware devices such as router or switches used are of low efficiency, the performance of the subnetwork is also decreased. The first is what are network commands. The Windows operating system provides its user with numerous built-in network troubleshooting commands. These commands allows its user to maintain the network stability of the system. Let's move on with network commands. Now let's look into some of the most important and mostly used network commands in the Windows prompt. The first one is ipconfig. This is one of the most basic network commands used in the Windows prompt. It gives an overview of the network settings for our system. Moving on, we have ipconfig all. This is similar to ipconfig, but it gives a more detailed view of the network settings for our system. Then we have ping. This command is used to check or test whether the destination host is available for exchange of services or information. Moving on, we have traceRT. This command provides the user with an overview of the path that has been taken by our IP address to reach the destination IP host. Then we have nslookup. This command is used when we have to look into the server data of a particular internet server, for example, google.com. Now let's look into some of the more network commands. This we have root. The root command provides the data of routing data packets in the system over the communication channel. Netsat. It is used to get an overview of all the currently connected networks from a system. Then we have ARP. The ARP command is used to display the ARP cache in an organized format. Then we have pathping. Using this command provides us with the output combination that is of both traceRT and ping to a certain extent. And in the end, we have systeminfo. This command provides us with the comprehensive overview of the device settings in a system. Now let's look into the demo for the network commands to better understand them. To execute the network commands, we have to access the Windows prompt. To do this, type cmd and you will access your command prompt. The first network command that we will execute is ipconfig. The ipconfig command displays network settings as an output. As we can see, this is the main connection that my system currently have with the IP address 192.168.1.3. Along with every IP address, a subnet mask is included. This is very important. As already told, ipconfig just shows an overview of the connection settings. But if we want to look into more detailed version of the network settings for our system, we use the command ipconfig all. As visible, ipconfig all command provides us with a much more detailed view of our connection settings, including DHCP settings, along with the lease obtained for our IP address, the default gateway, including the DHCP server settings. Also, details about the DNS server. Now let's take a look at the next network command in the list, that is nslookup. nslookup command is used to access the IP address of a particular website or a host through its domain name. This network command is helpful when we don't know the IP address and wants to know it, but we only have the domain name. Let's take a look. Let's clear the screen for much proper view. nslookup. By default, the nslookup command provides us with the data of our system, that is, the default server that my system is currently connected to, and the IP address of my system. To access some other website or host's IP address through its domain name, we have to write www dot, in this case, let's take google.com and press enter. Through this, from this part we can access the IP address that has been used by google.com. Let's try using some other domain name. For example, www.amazon.com. As we can see, the IP address, the alias, and the name from the amazon.com. Till this point, we have seen what is ipconfig command, ipconfig all command, and the nslookup. Now let's move on to the next command, that is ping. Ping command is used to check whether our system can access a particular website. Let's take a look. To come out of the nslookup command, do Ctrl C. Now let's try ping. To access the ping command, we will use the domain name www.amazon.com and press enter. After the execution of the ping command, we can see that our system sent 4 packets and the destination IP also received 4 packets. That means the loss is 0. This means that the Amazon website is accessible from our system and there is no loss of data during the transmission. In case if we don't have a domain name for a particular website, we can also use the IP address. For example, ping and followed by the IP address. In this case, let's take the Amazon again. The IP address is 23.33.245.99 and press enter. As we can see, the system has again sent 4 packets to the destination IP address and the destination has received 4 packets without any loss. Now let's move on to the next network command in the list. That is traceRT. The traceRT command is used to trace the path that has been taken by our IP address to reach the destination IP address, which is very helpful if we want to troubleshoot the path that has been taken. But before we use traceRT, we need a destination source. Let's try using nslookup and use the Facebook's IP address. Let's exit the nslookup command using Ctrl C and type traceRT along with the IP address of facebook.com, that is 157.240.228.35 and press enter. On execution of the traceRT command, we can see the number of routers or network devices that our system's IP address has to go through to access facebook.com. And we can see the number of hops that are available are 13. Let's see the number of hops our system has to take to access Facebook. And seems like the number of hops it takes to access Facebook from our system is 8. Through the use of traceRT command, we can see how many hops and what devices or router our IP address has to go through access a particular website. Now let's move on to the next network command, that is root command. Root command is used to access and manipulate the IP routing table of a system. You can access this command using route and print and this enter. As we can take a look, it provides us with the destination IP address along with the net mask, gateway, and interface. All these are necessary for a network programmer to take a look of any details that are regarded in the target or the destination IP address host. With this, let's move on to the next network command, that is netstat. This network command is used to access the connections that are currently available on a computer system through the TCP and UDP ports. To display the result, let's write netstat and press enter. From this, we can take a look the number of connections that are currently available or inactive, or in case closed to the netstat command. Now let's move on to the next network command, that is ARP. Let's clear our screen and use ARP. The ARP network command is used to access the IP addresses for a device along with their physical addresses. To use this, we have to write ARP. If you do this and press enter, you'll access the help mode for ARP command. To access the output, you have to write ARP-A and press enter. With this, we can take a look at the IP address along with their physical address and also the type of IP addresses they are. For example, the first one is a dynamic IP address, whereas the rest of them are static. Now let's move on to the next network command in the list. That is the path ping command. This network command is used to access the path that our IP address take for the destination host along with the calculation of loss of the data that has been transmitted over the communication channel. To do this, type path ping along with the destination source, that is, for example, facebook.com. And press enter. On doing this, we get the number of routers and the path that has been taken by our IP address to the destination host. Pathping command might take some time to execute. After the execution of the command, this is the whole result that we receive on a window. These 8 represents the path and the statistic represent the loss at each point of IP address during its transmission over the channel. Now let's take a look at the last network command in our list, that is system info. As the name suggests, system info is used to access or display the whole overview of a system device's setting. To do this, write system info and press enter. As we can see, all the data regarding my system device is displayed as an output. What is user datagram protocol? The user datagram protocol, commonly known as UDP protocol, is designed to be unreliable and connectionless in nature, which applies process-to-process communication model for data exchange between devices and is active in the transport layer of the OSI model and is used to transfer data and information related to internet services over the network channel. where process-to-process communication refers to the use of port numbers in the header format during the transmission of data over the network channel. As for connectionless, it means that the UDP format does not provide a established path for the data to transfer. Instead, it uses multiple different paths, which we will look into further in the video. Let's move on to the next heading. Features of using user datagram protocol. The user datagram protocol provides the network with various efficient and easy to understand network protocol features to apply over the data that is to be transmitted. Where the first feature of UDP is related to the working area. That is, the UDP model is a transport layer protocol of the USI model and is used to deliver best effort delivery options for the data transmission. Where the best delivery option refers that the protocol does not provide the sender will receive any acknowledgement from the receiver side for the data transmitted, or it does not provide any guarantee of data transmitted to the receiver side. Now let's move on to the second feature of user datagram protocol. The second feature represents the mode of delivery or connection that the UDP establishes for data transmission. The UDP protocol, as we know already, establishes a connectionless path. That means there's no actual virtual path for the data to be transmitted, so that the each data from the UDP format uses a random path available in the network channel and reaches its destination. Now let's move on to the next heading, that is UDP header format. The UDP header format comprises of two parts. First, the UDP header part, which is 8 bytes in size, and second, the data to be transmitted. Furthermore, the header part is divided into four different parts: source port, destination port, total length, and checksum, where each of the parts are divided into 16 bits. Let's take a look at the different parts of the header format in a little detail. The first one is source port number. It is a 16-bit value that is used to identify the port that is transmitting the data. Next is destination port number. That is used to identify the port number that will be receiving the data on the receiver end. Next we have total length. As the name suggests, this value is used to specify the total length of the UDP packet, including the UDP header part. And the last is checksum. This is a 16-bit value field and is used as an optional attribute. It is left empty if there is no need, or it is used in case where accuracy of the data is to be measured. Now let's move on to the working of the UDP protocol. To begin with, we have data from the sender side, which is enclosed with the UDP header for communication and data in the UDP header part. The next step is to hand over this data over to the IP section for encapsulation, with the IP header and data with the UDP header and data part. As for the last step, this part is handed over to the frame section, where it is transformed with the frame header and data format. Moving on, now let's transmit the data over the network channel for the receiver end to receive it. Over to the receiver side, first step is decoding of frame header part and data part into the IP section, which contains IP header and data section. Again, this IP packet is divided into UDP header part and data part, from where the message is retrieved from the data section of the UDP header format and is then received by the receiver end. Now let's move on to the applications of UDP protocol. Let's take a look at some of the features of the UDP protocol that provides applications to various network models. For the first one we have, it provides flow control and error control mechanisms to the network model, such as TFTP. Next, it provides faster transmission of data as there is no pre-established virtual path needed. So it is used for real-time services, live communication, and gaming services. Now let's move on to the last setting for this session, that is UDP versus TCP protocol. We will differentiate between UDP and TCP based on some attributes that are mostly used in a network model. And the first attribute is reliability. For UDP protocol, as we already know now, it is an unreliable in nature. That is, it does not provide any guarantee of data transmitted to the destination side is reached or not. As for TCP, it provides reliable and guaranteed data delivery to the receiver side. The next attribute is acknowledgement signal. The UDP protocol does not provide any acknowledgement from the receiver side to the sender side. Whereas in case of TCP protocol, sharing the acknowledgement signal is very important. If the acknowledgement signal is not shared by the receiver side to the sender side, the data exchange will halt. Let's move on to the next attribute, that is connection mode. As we already know now, UDP is a connectionless mode of service. There is no virtual path established for the data transmission to take place. Whereas for TCP protocol, it is a connection-oriented protocol. That is, a virtual path is needed for the data to be transmitted over to the receiver side or the destination node. The next attribute is error check system. In UDP protocol, basic check system is only used for error check. Whereas for TCP protocol, it is an extensive error check service. And along with error flow control mechanism included in the TCP protocol service. Introduction to the protocol. The stop and wait protocol is a type of flow control mechanism active in the OSI model of the data link layer. The transmission of data applies only to the noiseless channels, where a noiseless channel represents an ideal network channel where no frames are lost, duplicated, or hacked. Moving on, we have the stop and wait protocol is unidirectional in transmission of data. That is, either sending or receiving data will only take place at an instance. For the third point we have, the stop and wait protocol, as the name suggests, is when the sender shares a data packet to the receiver end. Then the sender side has to stop and wait for the receiver side to send an acknowledgement before it starts sending the next data packet. With this point, we are now knowledgeable about the working of the stop and read protocol at an elementary level. Now let's move on to the next heading. The next heading for the session is steps involved in the stop and wait protocol. The steps for this protocol are divided into two parts, sender and receiver protocol. Let's start with the sender side. The first step is to transmit one data unit at a time to the receiver end by the sender side. And the next step is to transmit the next data until only after we receive the acknowledgement from the receiver end. Now let's move on to the receiver side. In receiver side, step 1 is to receive the data and use the data that is being sent. Then the second step is, after the data has been used by the receiver side, it will send the acknowledgement to the sender side for further data transmission. This is how the transmission of data takes place in the data protocol. Now let's move on to the next heading, that is working of stop and wait protocol. Using the previous two headings, we can easily determine the steps involved in this working. Let's take a look. To begin with, we have two sides, the sender and the receiver side. The first step is to send the data from the sender side to the receiver end. And after the receiver side has used the data, it will send the acknowledgement signal. Meanwhile, the sender side has to wait for the acknowledgement signal. Only after it receives the acknowledgement signal will it send the next data packet. Now that the sender side has sent the data for the second time, the receiver side will use this data and then only share the acknowledgement signal. This process of sending data from the sender side to the receiver side and receiving acknowledgement from the receiver side to the sender side continues for n number of times according to the given scenario in the network channel. Now let's move on to the next heading, that is also the last heading for this session, that is drawbacks of using stop and wait protocol. The first drawback of using this protocol is the loss of data. This issue can arise when transmitting data from the sender side to the receiver end. It may be due to any issue, due to hacking attempt, or network disruption, or any other network related issue. Then, this can also arise when receiving acknowledgement from the receiver side. Now let's move on to the second drawback. The next issue is related to acknowledgement transmission, that is, during the transmission of acknowledgement signal, due to the network issues, the acknowledgement signal is disrupted and the transmission is terminated. This can arise again due to any reasons that are occurring in the network channel. Now let's move on to the last drawback for this heading. The last issue occurs due to the delay in transmission time of the information. Time delay drawback can occur on either side of the transmission, that is, during data transmission or the acknowledgement transmission. What is a protocol? As we know, in a networking concept, protocols refers to the rules and instructions that governs the data transmission between different network models and devices in a communication channel. The data transmitted using protocols is easily handled and is reliable to use, as well as it provides a secure channel for the data to be transmitted. Now let's move on to the different types of protocols available in a network channel. The protocols available in a network channel can be divided into two different types: noiseless channels and noisy channels, where the noise part refers to any external interference, data error, or duplicate transmission in the network channel. Furthermore, noiseless channels and noisy channels can be divided into subdivisions. Let's take a look at the noiseless channels first. Noiseless channels can be divided into two types: simplest type and stop and wait type, whereas noisy channels are divided into three subdivisions: stop and wait ARQ, go back and ARQ, selective repeat ARQ. In the noisy channel, go back and ARQ and selective repeat ARQ are the ones that apply the sliding window protocol for data transmission over the network channel. Now let's look into some information regarding sliding window protocol. To begin with, the sliding window protocol is a technique that allows the share of multiple data frames in a network channel, where the number of frames shared is determined by the window size assigned to the network channel. Also, the frames sent during transmission are assigned with a sequence number for efficient frame transmission in the communication channel. Till this point in the video, we have already learned about the definition of what is the sliding window protocol. Now let's look into the working steps of the sliding window protocol. To begin with, we have a sender side and a receiver side in the network channel. Then we require the frames, where each frame is given a sequence number. For this example, we are using 0 to 8. Which means a total of 9 frames are available at the sender side. Then using the window size, we determine the number of frames that can be shared at an instance. For example, we'll be using 3 as the window size for this example. Let's start with sending the first frame, that is 0, to the receiver side. After the frame is sent, a sliding window appears on the number of frames. Now let's move on to the next, that is frame 1. The point to be noted is, before receiving any acknowledgement, we have to send all the frames that are available according to the window size. That is, for this example, the window size is 3. That means we have to send 3 frames before we receive any acknowledgement from the receiver side. Let's send the last frame, that is frame 2. Now we have to wait for the receiver side to send the acknowledgement signal to the sender side before we can send the next frame. Now that we have shared the maximum number of frames, the receiver end will share the acknowledgement signal for frame 0 with the sender side. After this acknowledgement is received by the sender side, we can share the next frame in the list, that is frame 3. After the frame 3 has been sent, see the positioning of the sliding window. The sliding window now changes from 0, 1, 2 to 1, 2 and 3 frame. This positioning of the sliding window represents that 0th frame has already been acknowledged by the receiver side, whereas the 3rd frame is sent for acknowledgement from the receiver side by the sender side. And similarly, we have to do the same pattern for the next 2 frames, that is frame number 1 and frame number 2. Now, the sender side will receive the acknowledgement for frame 1 from the receiver side. And we can send frame 4 from the sender side to the receiver side. Now see the movement of the sliding window. The sliding window changes from 1, 2 and 3 frame number to 2, 3 and 4. Similarly, we can move on to the last frame. Now let's draw some simple conclusion from all the working steps we have seen so far. To begin with, frame number 1 and 0 represents the acknowledged frames, whereas the frames within the sliding window represents the frames that are waiting acknowledgement, whereas the remaining frames 5, 6, 7 and 8 are not yet shared with the receiver side. Now let's move on to the next heading for the session. Difference between stop and wait protocol and sliding window protocol. The first comparison is on the basis of working mechanism, where the stop and wait protocol is designed to send the data frame at a single time and wait for the receiver to send the acknowledgement to share the next frame. As for the sliding window protocol, sender can send multiple frames simultaneously and then wait for the corresponding acknowledgement from the receiver end. Let's move on to the next comparison, that is based on the window size. On the basis of window size, the stop and wait protocol is always fixed at 1. As for sliding window protocol, as we saw in earlier slides, it varies according to the scenario in the network channel. Let's take a look at some other comparisons too. The next comparison is based on efficiency and time delay. As comparison on this basis, the stop and wait protocol is efficiently low and suffers from more time delay. As for sliding window protocol, the efficiency is higher than the stop and wait protocol, which provides lower time delay during data transmission. Let's move on to the last comparison. Sorting and transmission of data. For stop and wait protocol, sorting is not required and it applies half duplex system for data transmission. As for sliding window protocol, we require sorting for better efficiency and is full duplex in nature. Let's begin with the sliding window protocol. Sliding window protocol is a method to share multiple data frames at a time in a network channel. The frames shared in the network are based on the window size assigned beforehand in the network model. As for the last point we have, each of the frames are assigned a sequence number for frame transmission and also to achieve more efficiency in the network channel. Now let's look into some information about the Go Back and ARQ protocol. This protocol applies the sliding window method for transmission of data in the network channel, where n in the protocol refers to the window size assigned in the network model. As for the term ARQ in the protocol refers to the automatic repeat request, which means the sender side will send multiple data frames to the receiver side according to the assigned window size. And only after it receives an acknowledgement from the receiver side will it continue to send the frames from the sender side. Moving on, let's look into some important points regarding the protocol. As to begin with, the method applied to share multiple frames from the sender side to the receiver side is known as the protocol pipelining, where each frame is assigned a sequence number for proper transmission of data in the network channel. Now let's move on to some other important points. As we already know, the n in the protocol refers to the window size, that is the maximum limit of frames that can be transmitted from the sender to the receiver side before reaching the acknowledgement for the previous frame. And in case if the transmission of the acknowledgement of a frame is not received within a certain time period, then all the frames from that sequence number are to be retransmitted in the channel. This point is to be remembered properly because this will be the key point in solving a question related to Go Back and ARQ protocol. Now let's move on to the working of the protocol. To begin with, we have a sender side and a receiver side, along with the sequence number, the window size for the network channel, and the number of frames will already be assigned in the network. Now, by applying the sliding window protocol, we will send the first 3 frames from the sequence continuously, which will be frame number 0, frame number 1 and 2. This is assigned according to the window size. After sending the frames, we will have a sliding window over the sequence numbers that are 0, 1 and 2. After the frames are sent to the receiver side, it will use the frames and send an acknowledgement signal to the sender side. That would be 0 for the first time. After which, we can share the next frame, that will be frame number 3, from the sender side to the receiver side. After sending frame 3, the sliding window from sequence number 0, 1 to 2 will shift over to 1, 2 and 3. And similarly, for frame number 1, we will receive the acknowledgement signal from the receiver side to the sender side. And then we can share the next frame, that is frame number 4, from the sender side to the receiver side. And the sliding window will shift over from sequence number 1, 2 and 3 to over 2, 3 and 4. As for the next frame, that is frame number 2, when we receive the acknowledgement from the receiver side, there is a catch. For any network issues, the acknowledgement is not received by the sender side. So in this case, as discussed earlier in one of the important points, the sender side will not transmit frame number 5. Instead, it will retransmit frame number 2, 3 and 4. Where the second frame is the one which did not receive the acknowledgement, and all the frames sent after second frame is to be retransmitted along with it, that is 3 and 4. To much better understand the solution for the example we'll be solving later in the video, it is suggested that you watch the steps involved in the working of the Go Back and ARQ protocol again. Now moving forward, let's take a look at some of the advantages and disadvantages of using the protocol in a network channel. For advantages we have, it increases the efficiency of transmission of frames. It also allows multiple frames to be sent at once. And the time delay is low for sharing the packets. As for disadvantages we have, the retransmission of frames in case of an error in the network channel is a very difficult work. And it also requires the storing of frames on the receiver side that it receives from the sender side. Now that we have learned everything about the Go Back and ARQ protocol, let's take a look at the much awaited working example for the same. Let's take a look at the problem statement. In a given network, the number of frames provided is 10, with the window size assigned as 3, and for every fourth packet is lost. Find the total number of messages or frames sent from the sender side to the receiver side. From this question, we can get three main parts, that are the number of frames that are given is 10. As for the window size is 3, and every fourth packet is lost. Let's take a look at the options. Option A 27, option B 25, option C 22, and option D 29. I'll give you guys a moment to take a look at the question again. Now let's move on to the solution. As usual, we have the sender side and a receiver side. And according to the question, we have 10 frames. Numbering the frames sequentially, we have frame 1 to frame 10. And then according to the question, we have window size as 3. Now, using the sliding window method, we'll send the first 3 frames, that is frame number 1, 2, and 3, from the sender side to the receiver side. That will be like this. After sending the frames, we'll wait for the receiver side to send the acknowledgement. And a sliding window will appear on frame number 1, 2, and 3. Now the receiver side will send the acknowledgement for frame 1 to the sender side. And using this, we can send frame number 4 from the sender side to the receiver side. And a sliding window appear on 2, 3, and 4 sequence number. And similarly, for frame number 2, we'll send the acknowledgement from receiver side to the sender side. And send frame number 5 from sender to the receiver side. And a sliding window appears on sequence number 3, 4, and 5. Then again, for frame number 3, we'll send the acknowledgement from the receiver side to the sender side. And send frame number 6 from the sender to the receiver side. And a sliding window appear on frame number 4, 5, and 6. Now let's move on for the next frame for acknowledgement, that is frame number 4. For this frame, according to the given question, every fourth frame is lost during transmission from the sender side to the receiver side. That means no acknowledgement will be sent from the receiver side to the sender side for frame number 4 in that regards, or any other frame that are sent after frame number 4, that is frame number 5 and frame number 6. Similarly, frame number 5 and frame number 6 will also get discarded. Now, let's retransmit according to the Go Back and ARQ protocol. Frame number 4, frame number 5, and frame number 6. After retransmission, frame number 4 will get acknowledged by the receiver side to the sender side. That means we can send next frame, that is frame number 7 from the sequence order. And the sliding window appears on frame number 5, 6, and 7. Similarly, let's move on to frame number 5. But before we do that, let's count the position of 5th frame in the transmission order. 1, 2, 3, 4, 5, 6, 7, and 8. That's correct. When we count the position number for any of the frames from the beginning, we use sequence, not the sequence number given by the question. That means fifth frame is at the position number 8 from the beginning. That means according to the question, it will get lost during the transmission from sender to the receiver side. Similarly, frame number 6 and frame number 7 that was sent after fifth frame will also get discarded. According to the go back and ARQ protocol again, we will retransmit 5, 6 and 7 frame number to receiver side from the sender side. After retransmission, frame number 5 will get acknowledged by the receiver side, and then we can share frame number 8 from the sender to the receiver side. And the positioning of the sliding window shift from 5, 6, 7 frame to 6, 7 and 8 sequence number. Now let's move on to the 6th frame. But according to the positioning order, position of the 6th transmitted frame is number 12. That means it will get lost during transmission from sender to the receiver side. And similarly, frame number 7 and 8 will also get discarded by the receiver side. And again, applying go back and ARQ protocol, we will retransmit frame number 6, 7 and 8. On retransmission, frame number 6 will get acknowledged by the receiver side, and we can share frame number 9 from the sender to the receiver side. And the sliding window will shift from sequence number 6, 7 and 8 to 7, 8 and 9. Now let's recount the position of the next frame, that is frame number 7 from the beginning, and that would be 16. That means frame number 7 will get lost during transmission from the sender to the receiver side. And similarly, frame number 7, 8 and 9 is to be retransmitted according to the go back and ARQ protocol. Now similarly, following all the previous steps, we can complete this network model using go back and ARQ protocol. But this is a work you guys have to complete and find out the total number of packets that were transmitted from the sender to the receiver side, and give your answers in the comment section.
Let's start off with question 1. What is the OSI model? Explain the different layers of the OSI model. OSI largely is a theoretical model utilized to understand networking and how data packets are created and how they are being processed by a computer. This is normally used by the TCP/IP, the Transmission Control Protocol over Internet Protocol software suite. So OSI is known as the Open Systems Interconnection model. It is a reference model that describes how applications are going to interact via the computer network. There are 7 different layers that we need to understand. They are as follows. So in this diagram, there are these 7 different layers. We start up from the bottom. First is the physical layer, the data link layer, network layer, transport layer, session layer, presentation, and application. When such a question is asked in an interview, it is not only that we identify these 7 layers, explaining what the OSI model is in the first place, we then try to identify these 7 layers and we give a brief description about each and every layer. If there are any additional questions, they will come after this basic question. So let's start off with the physical layer. This is the lowest layer of the OSI model. Now this is where any and every physicality of your computer comes into the picture. So it could be a network interface card, it could be an RJ45 or a Cat5 cable, anything that allows data to be transmitted physically from your machine to another machine. Next comes the data link layer. So on the data link layer, as far as networking is concerned, we just need to understand that data packet is encoded, decoded into bits at this layer. This is also the layer that deals with MAC addressing. So the physical address of every network interface card, which is the MAC address, which is utilized to route data packets over the network. This is where the MAC address resides on the data link layer. The next layer is the network layer. Here datagrams are transferred from one to another. The function of this layer are routing and logical addressing. The moment we talk about routing and logical addressing, IP addresses come into the picture. IP version 4, IP version 6. So network layer will deal with IP addressing and the routing of those packets. Then comes the transport layer. This is the layer responsible for end-to-end connections. That automatically signifies that this is where TCP and UDP will be working. TCP stands for Transmission Control Protocol, UDP for User Datagram Protocol. TCP is a connection-oriented protocol, whereas UDP is a connection-less protocol. These two protocols are utilized to establish connectivity between two machines. TCP is a more reliable method of connectivity because there are a lot of packets that are sent across to verify that the data has been sent, data has been received, and so on and so forth. Whereas UDP is a connection-less protocol where data is just dumped without verifying whether the receiver actually receives that data or not. So, in a nutshell, on the transport layer, TCP and UDP make their appearance, and this is where that functionality lies. Then comes the session layer. This controls signals between the computer. It establishes, maintains, and terminates connections between processes. So in the transport layer, we talked about TCP and UDP. UDP being a connection-less protocol where data is just transmitted without verifying whether the receiver received that data or not. Whereas TCP, we studied, is more of a reliable protocol. Thus, there are different packets, signals that will be sent across to verify that data has been transmitted, it has been received properly, and then the next segment of that data is being sent. So those control signals are established using the session layer. So the three-way handshake of TCP, the acknowledgement packets, and those kind of packets will be taken care of on the session layer of the OSI model. Then comes the presentation layer. The presentation layer is responsible to translate data into the application layer format. So the formatting, right? MIME or encoding that is being utilized, the UTF-8 character set that we utilize for presentation, encryption mechanisms, all of these work on the presentation layer. And finally comes the application layer, where the application itself uses a particular protocol so that the other machine on the receiving end, the application on that machine will be able to understand what the communication was about, right? So in a nutshell, if I start from up top, the application layer will deal with any of the data that the application is generating. So maybe a user input, you're logging in, you're typing the username, password, all that data will be constructed, let's say, into an HTTP or an HTTPS format. That's where your application layer comes into the picture. Then the formatting of which into UTF-8 and the encryption of which would be done at the presentation layer. Then this transport layer and the session layer would kick in to establish a TCP session, do the three-way handshake, establish that connectivity. IP addressing would be done on the network layer, MAC addressing would be done on the data link layer, and when everything is ready on the physical layer, the packet will be sent out. At the receiving end, the packet will be received on the physical layer, and then all these layers will be reversed, and finally at the application layer, the data would be presented to the application, who would then execute it and showcase it on the screen of the recipient. So this is the way you want to explain this question. You want to be very concise, precise about what you're explaining. You don't want to go into too hypothetical scenarios. You don't want to dilly-dally with the layers. You just want to give the basic functionality, want to demonstrate that you understand what the OSI layer is, how the computer functions, and you want to move on from there. If the interviewer has any further follow-up questions, they will ask those specific questions. So that's question 1. Moving on to the question 2. Question 2 is define unicasting, multicasting, and broadcasting. Now this is a question which can be very lengthy, but again, most of your interview questions are designed that way. It's basically to understand how much conceptually you are aware about these technologies. So you have to be very concise. Don't go rattling about technology too much, but in a concise manner, just try to explain what these things is. So when data is being transmitted over a network, it can be transmitted either in one of these particular manners. It can either be a unicast, multicast, or a broadcast. So what is unicast? Unicast is when a message is sent from a single user to a single receiver. So one to one, right? So one machine talking to another machine and nobody else. So also known as point-to-point communications. One point to another point. If you have to send information to multiple receivers, then you will have to send it using multicast, right? So this is where your multicast networking comes into the picture. So in our case, let's assume it's a network where there's a class C network, approximately 255 odd machines. And within these, there are two machines that want to talk to each other. If they want to talk between each other, it would be a point-to-point communication where they will utilize unicast, where only these two machines will have visibility of that conversation and the other machines will not even realize that this conversation is taking place. If one machine wants to talk to multiple machines, then the multicast comes into the picture. As the name suggests, in this mode of communication, data is sent from one or more sources to multiple destinations. Multicast uses the Internet Group Management Protocol, also known as the IGMP protocol, to identify groups. So under this IGMP protocol, various groups are created where machines are subscribed to those particular groups. And whenever a message needs to be sent through those groups, it will be identified by the IGMP protocol, and then that particular message will be sent to those multiple machines that are members of those particular groups. And then comes the broadcast. The third method is known as the broadcast. As it says, it is going to broadcast to all. So this is one to all, that is communication between a single user, and it is going to be sent to all the machines in that particular network. Right? So the three ways: unicast is one to one, multicast is one to many, and broadcast is one to all. Then question number 3. What is DNS? DNS stands for Domain Name System. It is like the internet's phone book that is responsible for mapping the domain name into its corresponding IP address. And let me give you an example over here. Whenever we go and open up, let's say, a browser, a Google Chrome browser, we type in www.google.com and then we press enter, and magically Google comes in front of us, the website rather. Now, how does the computer know who Google is? Because as far as we are concerned, humans understand Google and words like that. Computers don't. Computers deal with binary, zeros and ones, right? And as far as internet is concerned, they will only deal with IP addresses and MAC addresses. So how does a computer know how to find google.com and where is it located? So the moment we type in the browser window, in the address bar, google.com and press enter, a DNS query is generated automatically by the browser, where a packet is sent to our DNS servers asking what the IP address is. So in short, DNS resolves domain names to their corresponding IP addresses. There is a DNS server which will have this index, a database of all the domains associated with their IP addresses. If one particular DNS server does not have that information that you're looking for, it may query another DNS server who may have that particular response. So the first thing is, when you type in domain name, it gets resolved with the DNS. It identifies the IP address corresponding to that particular domain name, and thus allows the computer to route that packet to the particular server where that domain name resides. So in this scenario, if you look at the screen, on the local PC, you have typed in cybersecurity.com. There is a DNS resolution, that a query that goes to the DNS server. What is the IP of cybersecurity.com? The DNS server looks it up in its particular database. If it has the corresponding IP address, it will then respond back. The IP address is 172.17.252.1, after which the packet is sent off to cybersecurity.com. Moving on to question number 4. What is a firewall? Now, this is a very good question, and normally a very basic answer that I've ever heard is that a firewall is a hardware and a software firewall. But that's the functionality of a firewall. That is how you can install a firewall. But there are different types of firewalls, and there is a specific functionality that a firewall is created for, right? So a firewall is either a hardware or software, but its responsibility is for blocking either incoming or outgoing traffic from the internet to your computer. They secure a network. So essentially, the firewall will allow a connection to happen or disallow a connection to happen. It won't go beyond that. That's the basic functionality of a firewall. Okay. So based on the configurations that you have done, based on the rules that you have created on the firewall, it will then, based on those rules, identify whether some traffic is allowed in that network or some traffic is to be blocked from entering that network. So as the screen shows, the firewall rules will analyze whether the traffic is good. If yes, it will allow. If the traffic is bad, it will block the traffic and not allow that connection from happening in the first place. Now, there are a few common types of firewalls that also need to be included in the answer to this question. And the first one is a packet filtering firewall. These are the most common types that you will come across, which analyze packets and let them pass through only if they match an established security rule set. Now here people do get confused when we say that we analyze packets. People think that these firewalls will analyze the contents of that packet, which is not correct. When a definition for a packet filtering firewall says that these firewalls analyze packets, it means that they are only analyzing the source and destination IP addresses, port numbers, and the protocols that are mentioned in those packets. These firewalls do not have the capability of deep packet inspection, or DPI as it is known. If that capability comes into the picture, you're basically looking at an intrusion detection system or an intrusion prevention system in today's world called as a next-gen firewall. Okay, so a packet filtering firewall essentially will only analyze data packets for its source and destination IP addresses, port numbers, and the protocol that is being utilized. It will then map that information to the rules that are there on the firewall, and based on those rules, it will either allow that connection to happen or disallow that connection from happening. The second type is a proxy firewall. These firewalls filter network traffic at the application level. So when you say application level, they work at the layer 7 of the OSI model. Packet filtering firewalls, since we have mentioned that they work on IP addressing and port numbers, will work on the network layer of the OSI model. Also on the transport layer, because they also look at protocols. Proxy firewalls will work at layer 7, which is the application layer of the OSI model, and will deal with application level protocols such as HTTP, HTTPS, FTP, SMTP, and so on and so forth. And the third one is a stateful multi-layer inspection firewall. These filter packets at the network, transport, and application layers. So they basically do the job of the first and the second type of firewalls. The packets are compared to known trusted packets. But now the first question is, if there is a stateful multi-layer inspection firewall, why do we have type 1 and type 2 firewalls like packet filtering and proxy firewalls? That is because that is how the firewalls have evolved. We started off with the packet filtering, then we added functionality to it, and so on and so forth. So if a question comes, what is a firewall? You start off with the option saying it is a hardware or software. This is the responsibility, the functionality of a firewall is to allow good traffic and disallow bad traffic based on the rules that have been configured on the firewall. And then you've got basically 3 types of firewalls: packet filtering, proxy, and stateful multi-layer. And just include a brief description of each of these firewalls.
If getting your learning started is half the battle, what if you could do that for free? Visit SkillUp by Simplilearn. Click on the link in the description to know more.
Then moving on to question number 5. What is a VPN? VPN is also called a virtual private network. It is a connection between a VPN server and a VPN client. So it basically creates an encrypted tunnel between the client and the VPN server, which is then utilized to secure the connections that you're making with the internet. So as you can see in the diagram, the user has a VPN client installed on their machine. The VPN client then creates an encrypted tunnel to the VPN server. And through this tunnel, encrypted data is transmitted, which can then be processed by the VPN server, sent to the internet. Information can be received back by the VPN server. The VPN server will encrypt that data back and send it back to the user. So if there is a man-in-the-middle attack that is happening, or a hacker trying to eavesdrop on the communication mechanism, they will not be able to do so because of the encrypted tunnel. It is very difficult to decrypt this or hack through this encrypted tunnel. It is possible, but it is very difficult to achieve that. Moving on to question number 6. What are the advantages of distributed processing? Now, before we go into advantages of distributed processing, we first have to understand what is distributed processing. So it is a term which describes various computer systems that use more than one processor to run an application. Here, multiple computers across different locations share the same processor. The advantages of distributing processors are as follows. But before we go into the advantages, distributed computing is basically where multiple machines will pool their resources together to run a singular application. So an application that has multiple resources and can scale up and scale down as and when required. The advantages are that it can be very useful in data recovery. For example, RAID, where you're striping data on various hard disks. It is reliable, it is cheaper, lower cost can be achieved, and it is easy to expand because of the scalability factor that we just talked about. If there is loss of data in one computer, it can then be recovered by another interconnected computer. And one of the examples would be blockchain in today's world, right? What is blockchain? That this data is created live and stored on a connection of computers. So if one of the computers goes offline, the other computers in that network will still have that data, and the blockchain will still function without any issues. The second point, a glitch in one machine does not affect the processing, as there will be multiple other machines like we discussed in the blockchain. Several cost-effective mini computers are used instead of costlier mainframe machines. So instead of having a server bank, I can have multiple machines interconnected together, and they can function in that particular blockchain or for that particular distributed processing mechanism. Depending on the amount of data processing, more computers can be attached to the network. Thus, you can increase the number of computers that can be a part of that blockchain, or you can reduce them as and when necessary. Moving on to question number 7. What is TCP/IP? TCP/IP, or Transmission Control Protocol over Internet Protocol, is a set of communication protocols that are used to interconnect networking devices on the internet. This protocol defines how data should be transmitted over the internet by providing end-to-end communications. So essentially, if you want networking to be established on your machine, you will need TCP/IP. Without TCP/IP, there will be no work groups, there will be no domains. Basically, your interconnectivity will go for a toss. TCP/IP is a software that once installed on your machine will then interact with the hardware, which is your network interface cards, and then your switches, wires, cables, and all those, through protocols that have been already pre-configured in it. So within the TCP/IP suite of softwares, you will have all the protocols, all the functionality of the OSI layer, and each and every protocol that works on each and every layer will be predefined and pre-configured to work in a particular manner. The Internet Protocol is all about routing each individual packet to make sure it reaches its destination. So with the TCP, you're talking about the protocols that will allow you to format the data and generate it so that you can communicate it over the network. The IP will then deal with the routing of those packets so that the packet can be routed to the correct computer and be received by the recipient. So the TCP/IP model is the compressed version of the OSI model. The 7 layers will get converted into 4 layers: the network access layer, internet layer, transport layer, and application layer. Going on to question 8. What do you mean by ipconfig and ifconfig? Both of these are commands, the first one on a Windows machine, the second one on a Linux machine. So ipconfig is known as the Internet Protocol Configuration. This is a command that is used on the command line interface of Microsoft Windows to view all the adapters and the configuration of each and every adapters for their network interfaces. So as you can see on the right hand side in the command prompt screen, if once you type in the ipconfig command on the C prompt and press enter, it will give you a list of all the adapters that are there. So you can see wireless LAN adapter, local area connection, the media is disconnected, it doesn't exist. At the bottom you will see the Wi-Fi connection, wireless LAN adapter, and it can give you the IP version 6 IP address, IP version 4 address, the subnet mask, and the default gateway. So this is the configuration that allows the machine to know on what network it is on, what is the default gateway for communicating to the internet, what is the subnet mask, so how many computers may exist in that particular network, and what is the IP address of that specific computer so that it can communicate across the network as well. ifconfig is the same thing on a Linux, Mac, or Unix operating system. So the command will also give you the list of interfaces and the configuration of each and every interface. It is used to configure, control the TCP/IP network interface parameters from the command line interface. It allows you to see the IP address of these network interfaces. So here you can see the WLP19S, the IP address being 192.168.43.215, subnet mask being 255.255.255.0, with the broadcast being 192.168.43.255. Question 9. What is the difference between a domain and a work group? This can be a very interesting question and can be a very lengthy question at the same time. A work group is nothing but a decentralized network where you have interconnected multiple machines together, and each machine acts in its own individual capacity. Thinks of itself as a server, right? So a decentralized network, every user manages the resources individually on their PC. So local users on their own PCs managing the network shares, what can be shared from that particular machine, what data should be shared, should not be shared, to whom it can be shared with, and so on and so forth. It is good if you've got a small network, a few machines altogether, and you want them to interact with minimal management effort, right? So each user will decide what they want to allow other users to see on that particular network. And all of them would be connected over a LAN, a local area network, either a wireless or a wired one. So if you look at your home Wi-Fi right now, that is one of the best examples of having a work group. The domain, on the other hand, is a centralized network model. So in a corporate environment, whenever you go there and you got a domain-based username and password, which when entered onto a particular machine gives you access to the entire network or whatever applications and whatever resources have been allocated to you, that is where the domain comes in. So it also uses a single sign-on mechanism for all the resources that are to be made available to you. Whereas in a work group, you're a local user only meant for that particular computer, right? So coming back to the domain, it is an administrator who's going to manage the entire domain and all of the resources connected to the domain. The resources could be switches, routers, servers, data stores, applications, web servers, mail exchange servers, and so on and so forth. So all of these are administered by an administrator through the domain. It is the most reliable and the optimum solution for a large network where multiple users are going to interconnect and share that data amongst each other, right? The computer can be connected to any network. That means you can be on the internet, and through the internet using a VPN, you can connect to your corporate network, authenticate in, and get access to whatever resources you are allowed to access. Whereas in a work group, you have to be a part of that network to access that particular network. If you change your location, you go and connect to another Wi-Fi, you will lose access to your previous Wi-Fi. Then the last question for the networking section, what is data encapsulation in networking? Data encapsulation refers to the process of adding headers and trailers to the data. The data link layer binds each packet into a frame that contains the hardware address of the source and the destination computer. So in this example, when you're talking about data encapsulation, we have talked about how data that has been created by the application layer would have a header and a trailer that will give the various informations of where that data needs to be sent. So the hardware address, which is the MAC address, comes into the picture and gets added to the header, and the IP addresses, port numbers, and all of those things would then be added to this trailers as well, so that the data can be then routed to the intended recipient of that particular communication.
With this, we are completed with this full course on computer networks. If you have any questions regarding the topic, you can ask them in the comment section. Thank you for watching.
Hi there, if you like this video, subscribe to the Simplilearn YouTube channel and click here to watch similar videos. To nerd up and get certified, click here.